Today, in this talk, I want to talk about building LLM agents in production and why I feel Go is a wonderful language already to build production LLM agents. So a quick introduction about myself. I'm a graduate student at University of Illinois, where I spend time researching how to make performant LLM systems. And before this, I spent a lot of time developing distributed systems and backends, which is what got me started with Go. This is my first GopherCon, so I was one of the few people who raised my hands, and hopefully the first of many. So you might have heard of this thing called AI agents that are apparently transforming our industry. And in case you didn't get the memo, 2025 is supposed to be their year. But for some reason, we're still trying to figure out what exactly an agent is. So for this talk, I want to present a working definition of an agent to be anything that can perceive its environment and act upon it. So in the context of computer use agents like Claude Code, this environment will be the computer that the agent has access to, along with its terminal and its file system. And it can interact with this using tools that are available to it. And these are operations that enable it to read files and list directories. So an LLM agent then is just an LLM that you take and augment with extra capabilities that allow it to act in this special way. And I do want to mention that agents have existed for a while in artificial intelligence. But what LLMs are recently enabling is using their generalized reasoning capabilities to autonomously decide what next actions to take without requiring programmers to pre-specify every single scenario. And it turns out you can implement LLM agents very easily. It's just an LLM that you add tools to and just run a while loop over. And these tools are the interfaces using which LLMs interact with their environment. But still, it turns out there are a lot of agent frameworks that you could choose from to build your LLM agents today. And some might say more than actual use cases right now. And this space is currently clearly dominated by Python due to its ability to prototype rapidly and a very stable ML ecosystem. So why then should you be using Go to build your agents? So Go offers a lot of unique advantages that I'd like to mention today. Firstly, its very simple concurrency model allows you to spin off a lot of Go routines with low overheads, which can help you process concurrent LLM requests and tools with low overhead. You also gain a lot from Go's performance. Its compiled binaries will speed up your overall task execution, and an efficient memory management will make it easier to write code in production. And finally, as Cameron alluded to, Go is perfect for shipping these cloud-native applications. Static binaries simplify containerization, and Go's mature ecosystem helps us orchestrate agents at scale. And all of you are already aware of this. And so over the rest of my talk, you might think, oh, that's so obvious. Of course, you would use a Go routine there. And that's exactly what I believe Go's biggest unlock will be. These are things that we are aware work in production and will work in production for AI agent systems as well. So the way I want to go over these advantages in today's talk is by building out an LLM agent from scratch that will write code for us similar to Claude Code. I will then scale this out to a multi-agent system and explore the benefits of doing so in the process. And finally, I'll talk about how we can containerize and deploy these agents to production. So our goal today is to build a coding agent that can help us write code. And it will do so by exploring a code base and then updating files inside of it to make code changes. And to do this, I have a small, simple Go project set up. And in this project, there's a to-do comment hidden somewhere that I'll ask the agent to implement without actually telling it where it is. Before we get there, I want to throw some code at you. I'm sorry, I know it's only 9:35, but I want to show to you that just these 20 lines of Go code are all you need to build out an agent, at least a very basic agent. And despite all the agentic frameworks out there, I won't be using any of them today. I'll just use Anthropic's Go SDK because I want to show you how easy it is. So what's happening in this code is that we have an agent that's running a for loop, and all it does is it reads input from the standard input, and then it sends it to the Anthropic LLM as an Anthropic LLM call to get a response back. And then it just outputs that to the command line. So according to our definition that we set out, this is a very simple example of an agent that does not have any tools. So let's test it out. Let's see if 20 lines of code is what all this hype is about. So I have a repository set up on my machine here, which has this code loaded. And I'll build my code and execute my agent. And I'll just say, hey, Claude, I am demoing you at GopherCon 2025. What do you have to tell our wonderful attendees? And I'll ask it to be concise because it tends to ramble sometimes. Is the font okay, by the way? Thumbs up at the back.
Yeah.
Cool. All right, so it says, "Hey Gophers," and attempts a GopherCon emoji to the best of its attempts. It'll get there. So it's clearly very thrilled to be doing that. And I'm not I'm not being deceitful. Those 20 lines of code was all this it took to do this. But we want to take this a step further, obviously. We want to build a coder agent after all. And to give our agent the ability to read files, we need to add a read file tool. And I want to stress this, that you just need to implement 3 things to make this work. The first thing is you need to specify the input to our tool, which in this case will just be a path. Next, we write a simple Go function that can read a file. And this is bread and butter in Go. You just read the file from the operating system. The only caveat here is that your tool inputs are messages, because that's how LLMs speak to code, as JSON messages. And finally, you just pass along that tool whenever you make an LLM call. And this enables the LLM to potentially pick that tool. And it will be able to tell us during certain times that, hey, I would like to use this tool. Can you please execute it for me? And it's the role of the application developer to facilitate executing that. And to do this, what we do is, instead of just printing out the output like we did in the previous demo, we check whether the LLM is attempting to call a tool use. And in that green box there, if it's a tool use block, I just execute the read file function. And then we just append the tool results for storing it and sending it back to the LLM. And using a statically typed language like Go really helps write code like this for LLMs, because we can simply use the types to switch on them. And that's it. I do want to mention that to keep things manageable, I like to follow this pattern recommended by Thorsten Ball in his blog, which creates an agent struct. This reduces the amount of boilerplate code you have to write and encapsulate the tools, and as well as the way the agent takes input and writes an output back. So that's a lot of code. Let's see if this actually works. So I'll switch out to my other branch now, git checkout demo 2, and I'll build this again. So I should show you before I do that I have this simple Go project loaded up in a separate repository. And here on the multiply function, there's a to-do comment that I'm going to ask the LLM to implement. I'm not going to tell it this though. So I'll do this again. And this time I'll tell it, hey, there is a to-do comment in / simple Go project. Can you please implement it for me? And I know it's a very simple example, but if it can't even do this, our jobs are all safe. We'll be good. So the first thing it does is it lists files to find where the Go project is. And then it notices that there's a main.go as well as a utils folder. So it's listing files in the utils folder, and then it'll read files one by one. So the green text you see on the screen here are the tool calls, and the blue lines are when it reaches back out to the LLM. So now it read the math utils file, and here it recognized that it had a to-do comment, and it's executed a write file now. I didn't show this in the code, but I implemented the other tools similar to read file. And that's it. I have successfully implemented the to-do comment in the simple Go project, or at least it claims to do that. Let's verify it if it actually did that. And if I output the file again, it's actually implemented this here. Don't clap. It'll eat our jobs, please. You can't be that nice to it. But I do want to mention that and highlight that we didn't program a lot of code. We just gave the agent a bunch of tools to help it interact with the environment, and a simple pattern of observing, reasoning, and acting enables it to do a lot more. And I want to also bring forth one inefficiency that I conveniently skipped over, which is that when it's attempting to find out where exactly the to-do comment is, it reads every single file one by one. So it reads file utils and sends it to the LLM to figure out, does it have the to-do comment? It doesn't, so it reads logger utils, then it reads math utils. This is inefficient because the real bottleneck here is your LLM call, and you want to make sure that you minimize the network call over and also like real costs in terms of money. So as a programmer, you could think we could totally do that together, right? Why are we reading it one by one? And that is something you could do using concurrent tool execution. So this is the code that we were using earlier, where if there's a tool use block, we just execute the tool, and I use a helper function here. But we just invoke execute the tool and serially wait for it, synchronously wait for it, and then append the output of it. You could very conveniently switch this out to a Go routine in just very few lines of code. And in these 6 lines of code, all you do is invoke the tool execution in a Go routine and collect the result in a channel. And I also use a functionality of Anthropic's SDK, which is called parallel tool calling, which allows you to ask the LLM to return multiple tool calls in parallel whenever there's an opportunity to batch things. So to show this, I'll switch out to another branch, demo 2.5. And if I run this, and this time I'll just ask it to read a file. So this time I'm just going to ask it, can you find the function foo and simple Go project? And I'm lying to it here. There is actually no function like this, but we'll see how it does. So this time, if you see, it batches a list file and a read file together. And when it's figured out that there's a utils folder, it batches 3 read files at the same time. We execute all of them concurrently using Go routines, collect the data, and it's after searching through all the files, I did not find a function named foo. So that saves up a lot of time. It saves your cost, and it also helps you batch tool executions of one user request with potential LLM calls of other requests. And I'm excited for a talk later in the day today by John, who I want to see more optimizations that you could do to speed up LLMs. So our coder agent is accurate, it's fast, and it's amazing. And if there's any VCs in the crowd right now, I am looking for funding. But if you think about our agent, all that it's able to do right now is use information that is in its environment or stored in its weights in its LLM. If it's asked about things that are not in this, it won't be able to do it. And that might happen for things like internal documentation. One thing you could do is to fix this is by adding a tool for every single documentation that you would like to query in your agent. But this creates a few new problems. This does not scale very well. And with every additional tool that you add, it risks confusing your agent about which one it's supposed to call when. And it also can lead to a rapid increase in your context. This also requires a lot of careful prompt engineering to make sure your agent's task accuracy does not diminish when you introduce 20 new tool calls to it. A better pattern that has emerged over the past year is to use multi-agent systems. And what you do here is you consolidate all functionality to fetch documentation into a separate LLM agent. Let's call this the documentation agent for now. All you add then is a single tool call to the coder agent that tells it to invoke the doc agent. And this could be over as a remote procedure call or over the network. This architecture has a few benefits. The first one being modularity, because separate agents make it easier to develop, test, and maintain agentic systems. And if you start to think about this being developed as a product in a team, it helps to separate out multiple agents across multiple teams and maintain them. Having specialization also allows you to create expert agents focused on specific domains, which helps with the overall task completion and system performance. And finally, and most importantly in my opinion, this flexibility here. You can use the reasoning of the LLMs to decide when to compose which agents in what order. This allows us to build elaborate agentic systems that can compose smaller agents together on the fly. So our doc agent is going to be constructed very similar to before. It's almost identical to the coder agent, just with different tools. So the first one here is going to be search Go documentation, wherein I make an HTTP call to package.go.dev. I don't need to do this. I could use the GoDoc tool, but I just wanted to show calling this over the internet because that extends to anything. And then because of the pattern that I'd introduced earlier, I just pass along new tools to an agent. And this time I make one slight notable difference, that I read and write from and to the network as opposed to over the CLI. And also, I implement my invoke documentation agent tool on the coder agent, which allows it to communicate with our documentation. And that's it. And I want to demo whether that is enough to make our agents talk to each other. So if I can just get my pointer to work. The way I'm going to do this is I'll start up 2 separate agents this time. Git checkout demo 3. Go build dot. Oops. Okay. All right, so in this one, I'm going to start an agent of type doc. So that starts a doc agent on port 8081. And in this one, I'm going to start a agent type of coder, and I specify it where the doc agent is running. So I'll just verify whether this works fine. And this time, I'll ask it to fetch a coding sample for github.com/this go.env package. So this time, the LLM should ask it to invoke documentation agent, and we see the request going along to the doc agent in its terminal window. The doc agent internally uses its own tools, and this highlights an important pattern with multi-agent systems. The overall task can be multi-turn and very complicated, and the coding agent doesn't need to worry about that. As long as the final doc agent returns some response, that's good enough for it. And it does. So it uses this information, uses it in its tool call, and is able to write a coding sample for us. And I want to mention this extends to anything you want. You could create, especially with MCPs today, you could connect your agents to anything. So as I mentioned, a key feature of this system is that you can build out really flexible multi-agent systems. And to deploy this to production, you could deploy the entire system as a single binary. However, this might lead to certain problems because not every agent might have similar execution patterns. The documentation agent, for example, might be used by a lot of other agents, as well as standalone by users to fetch relevant documentation through a chatbot. And solving independent scaling is not a new problem. This is something that we have dealt with microservices extensively in the past. And Go's philosophy is perfect for this approach. Containerization, especially, can help solve this independent scaling challenge, and Go lends itself really easily, as we are aware, to containerization because of statically linked and compiled binaries, it being easily compiled to cross-platform, and also having a really mature cloud-native ecosystem. Especially for AI agents, I want to mention containers also have a much more important benefit of isolating your environment because you don't want to deploy agents that can generate LLM-produced code in production environments. So having a certain degree of isolation also really helps here. And to containerize this is all the Docker file looks like. You just go build your agent and then just run it inside a container. You can build a similar Docker file for both of those agents to get individual containers up and running. And to orchestrate our containers in production, we could use something like Kubernetes so that we don't have to manually worry about things like how one container finds an instance of another container to communicate with it. And I want to stress this, that there's a wealth of experience that we can build on if we start to do this. There's already a lot of established practices about how to scale web services using Docker and containers and Kubernetes. And we could totally borrow from that to deploy our AI agent systems. So if we do this, we'll be able to get a lot of benefits of auto-scaling and service discovery and load balancing. So for my final demo today, what I want to showcase is, wow, this was still running. Yeah, so I'll git checkout demo 4. And I should have a, let me check if my cluster is, oops. Kind delete cluster. So I will need a moment. I was supposed to do this before, but I'll need a moment to create and set up my cluster. So this will take some time. So what it's going to do is I'm going to be running these containers on kind. And this is currently setting up my kind cluster. And after this, it should take a quick moment to build my Docker files and load them onto my cluster. So it looks like the control plane is ready. It's building the first Docker file, which should be a quick build, hopefully. And now it's building the second one. And yeah, that's loaded now. And I can just deploy my containers over Kubernetes now. And the way I've set this up is because I hypothesize that our doc agent is going to be a lot more popular. I have created a service that has four instances of the documentation agent, and the coder agent service only has 2 instances. So it seemed like that worked. So if I do, I'll get rid of this. If I get my pods, that's up and running. We have 2 coding agents and 4 documentation agents. And if I make a quick curl over my network to my coding agent, so that might take a while, so I'll also get some logs from here and see if that works. So hopefully, like the previous demo, what this should do is internally, it should establish a communication with the documentation agent and be able to talk and figure all of that out without us telling it which exact container to talk to. And my follow does not seem to work all the time. Yeah, it did respond to us here. So it is working for sure. And if I could, yeah, I'm not sure why my logs are not showing up, but with very few lines of Docker file and a Kubernetes file that I have not shown you, you can have multiple instances of your agents running in production, and they can talk to each other in containerized environments. And finally, as a closing note, I want you, the key idea that I want you to leave all of you with is building agents in Golang is very easy. And if you choose to do this, you can immediately leverage a lot of existing production patterns that are well set over the past decade. As Cameron mentioned, there's a lot that we as a community can do to make sure Go is the perfect language moving forward in the AI age. And there are a lot of open source AI agent ecosystem libraries right now. So you don't have to contribute in the form of new libraries. Just using and sharing experiences through blogs are great contributions to make sure Go is great. Early experimentation can really help our community recognize areas for growth and collaboratively shape Go's role in the future of AI agents. So that's what I'd like to leave you all with. Thank you all for being a wonderful audience, and I hope you have a great GopherCon.